My name is Bill Brown. I'm going to talk to you today about my project, which is a GIS model used to predict the location of archaeological sites based on environmental variables. This study uses traditional suitability analysis, logistic regression, and Monte Carlo simulation to determine whether the 6 environmental variables explain late formative Hornado-Mogollon settlement patterns in southeastern New Mexico. The goal is to test whether specific environmental factors can be used to predict the location of undiscovered sites. So these two pictures right here are screen captures of the slope layer that I calculated from a DEM. And traditionally, archaeologists have seen earlier Mogollon people as living on this flat area right here. This is the basin. You can see the white stuff is very flat. Around 900 AD to 1100, there was it's thought there was a rainy period, and people moved up to these alluvial fans to do farming. You see, I've got the alluvial fan highlighted in purple here. And the reason they did that is they want to catch the precipitation runoff, for their crops, because they didn't have irrigation or anything. So I originally thought the slope would be the determining factor when it comes down to my environmental factors. So here's the study area, and the archaeological adaptation to the area was originally defined by Lamer in 1948. But you can see it's a very big area. It's one of the biggest for all the southwestern prehistoric groups. This is one of the most diverse, largest, and biggest natural environments of any of those prehistoric groups there. What I did was I looked at at first I looked at 5 environmental variables, then I added a 6th one. I looked at aspect and slope, and I used 11 DEM tiles, and I looked at land cover and precipitation, but it's from 1971 to 2000, so it's not going to be, really applicable to, how applicable it is to prehistoric times that's debatable. And I took 12, these were polygon vectors, but I converted them to rasters with soil type. And later I added proximity to streams, which I also made from the DEM. So this analysis was done in 3 parts. The first part was a traditional suitability analysis I did in ArcGIS Pro as part of my GIST raster analysis final project. And in parts 2, I took logistic regression. I did logistic regression in RStudio and used Monte Carlo simulation also in RStudio. And then in part 3, I took the values that I got in the quantified part 2 stuff, and I plugged it back into the ArcGIS Pro suitability modeler. So in part 1, the first thing I did was I took all these 11 DEMs and I mosaicked them into one large raster. And you can see here's the Hornado-Mogollon area from the previous slide showing the study area. And I didn't create a mask, but what I did was every raster, you have to snap rasters in the environment. So I snapped it to this, although I didn't create a mask. And so in the first part, I characterized the environment of a reference site. And this site is the Scorpion site that I worked on about 20 years ago now. And what you do in suitability analysis is you define an area, and then I used zonal statistics on the continuous variables to figure out what are the environmental characteristics of the reference site, and then I apply those values to the rest of the sites that I want to test. So this gives you some idea of, again, I thought that slope would be the determining factor, so I spent a lot of time trying to figure that out, although it really didn't turn out. And so what I did was I came up with a suitability ranking of 1 to 5, and I plugged these into weighted overlay tool, and I gave each one of these 5 variables a weight of 60%, and the other one's 10%. And then I would go down to each archaeological site, and I would just tally, by looking at the statistics, what the scores were, and then I would add them together, and so it comes up with soils at 60% is just the highest adding of all these variables. And so that's, here's my final workflow in model builder for the part 1. And so going back to what I was just saying, it shows that the soils are the most determinant factor. But you know, I'm only looking at like 6 or 7 sites, so it's just not really that. You know, well, anyway, the what I just got done doing shows that this is actually probably not the case. When I resumed work on the project, I decided I needed a proximity to streams layer, because that's probably in a desert. You're probably going to, you know, location to streams is probably going to be a critical factor in determining site location. So I took the DEM that I stitched together, and I applied the fill tool and flow accumulation and flow direction, and proximity to streams became the sixth environmental variable. And you can see I converted the raster into a vector layer of streams that overlays nicely across this of course the green stuff, which is actually the close land that is close to the streams. So I took R, and I took all my data, and I conducted logistic regression of the site locations. And what I did was I had problems in R because with the few number of sites that I had, I went from 7 sites in the part 1 of this analysis, and I expanded it to about 40 that I could find data on, and then finally to 80. But R would never let me run the regression because it kept saying I have too few sites. And so I ended up having to expand from, I originally wanted to look at Doña phase sites, but I had to expand to the later El Paso phase. So now I'm not looking at the one Doña, I'm looking at all formative era, which are farming communities across the landscape. So now I've got a total of 306 archaeological sites, and I did logistic regression on those site locations and the 6 environmental variables that I outlined previously. And then I created a predicted probability map of the 6 variables, and I ran a Monte Carlo sensitivity simulation. And then I took the variables the numbers that I got in these steps, and I plugged it back into the regression driven suitability, and came up with a more informed map. So the results of the regression showed that only two variables, the proximity to streams and precipitation, proved statistically significant. So streams is very significant at 58%, and precipitation was 42. So I plugged those. These are the values I plugged back in when I went back into Suitability Modeler. Now in Suitability Modeler, you have the option to, well, what it does is it creates regions of ranked suitability across a landscape, and it gives you the option to choose the area you want to look at. So this red here on the left, this is the entire Jornada region, and I came up with an idea. I'm not sure if it makes sense or not, but I carved out a little subunit, because it looked like the sites were bimodally distributed in these two, the alluvial fans of these two mountains right here. And so what I wanted, I just arbitrarily carved out this thing, which I call the Western Study Unit, when you can see it over here. And I wanted to see if I ran suitability model on this entire area, could I predict sites within here, within my Western Study Unit. And there are about, I think, 148 sites, and I'll get back to the results later, which are right now. So as I was saying, the only 2 variables that mattered were proximity to streams, which is strongly increases the presence probability, and precipitation, which slightly increased the chance of there being a site. And the Moran's eyes show that all the environmental variables are they exhibit significant spatial dependence, meaning that they're not randomly distributed across the landscape, so that similar values in any one of these will be located next to similar values in the same thing. So it's not, these things are not randomly distributed across the landscape. The Moran's eye for the residuals was about 0.79, and it suggests that there's something missing in my analysis, that the errors are not spatially, well, the errors are spatially clustered, and that I have not accounted for something important in my model. Okay, now these 2 box plots show that the sites, these are the known archaeological sites, and these are the predictions. So the known archaeological sites are scoring a little bit higher, but this overlap shows some gray area in the map, or in my model. So known archaeological sites over here, they have got a score of about 3.8, and the background, which is the 1,000 randomly sampled pseudo-present sites, is a little bit lower. So again, this model does predict, it's got some predictive power, but there's some overlap, which is preventing, well, it's got some gray area in it. This density curve shows that the real known archaeological sites peak around here, and the background peaks around here. So again, the model is showing some real predictive power, but in this area right here, it's kind of a no man's land. And now the Monte Carlo simulation, I ran 200 simulations on just randomly selected weights, and it shows that with a median delta median score of about 0.43 confirms that there is some real world difference, but it's not exactly perfect. These maps show the distribution of of all the variables across space in relationship to archaeological sites, which are in black. And this is a continuous probability surface. And again, it doesn't really show anything in green. Everything is kind of, fair to middling, as they say. But I went back and plugged in for the regression-driven suitability, and that significantly increased the amount of sites clustered around dark green and green, which are areas that are suitable. When I plug these variables into ArcGIS suitability modeler, you can see that precipitation, this chart shows how much of the area in the study area is covered by these variables. So precipitation is covering a lot of space, so it's creating a lot of suitability. And streams, they don't create that much space, but what space they are creating for suitability or make it a lot more suitable. And here, like I said, I decided to select 20 regions to show which regions across the landscape are suitable. And it shows consistently that regions 1, which covers about 317 kilometers or square kilometers, and regions 2, which covers about 327 square kilometers. These are the most, these are consistently the most. And so it's stable across all patterns that I ran. Here's the final suitability map that I did in the suitability modeler. And you compare it to the first one, you can see it greatly reduces the area of suitability, and they tend to be the most highest suitable areas are concentrated across my computed stream areas there. So these are the regions that I created in suitability modeler, and here's the entire Jornada region over here, and here is a close-up of my Western study unit. So what I did was that you can choose, like I said, you can choose the locate area in suitability modeler, and so I ended up with 148 sites in this little boot-shaped thing right here. I caught 31 of them, and I'm not sure if that makes any sense or not. But what I tried to do was apply the characteristics of these environment over here to see if I could capture sites in this little boot-shaped area. So basically, the conclusion is that wetter areas, especially areas near streams, they greatly, this is the driving environmental determinant, and none of the other ones really played out. So slope wasn't really a factor, although I thought it would be. But what I did find was that by using the quantitative methods in R, it greatly sharpened the ability of my suitability analysis, and the Monte Carlo simulations, I think they lend some validation that the model is it's pretty consistent. So any questions?